beings, little humans who've been quarantined or maybe didn't do so good on your test. We're going to review with you for this. So, Chapter 7, Big Bang. Little review in chemistry. Hopefully you remember what matter and atoms are. The matter is anything that has mass and takes up space. And atoms
are the smallest unit of matter, made up of 3 subatomic particles: protons, which are
positive,
neutrons, which are
negative,
and electrons, which are...
I said that wrong.
We did that on purpose because
Whoops.
that's what kids always do.
Yep.
They get it mixed up. So this is the hard part, so don't mess it up. Protons are
Positive.
neutrons are
Actually neutral.
Neutral. Yes.
Yep.
And electrons are...
Negative. Those are the negative ones.
Yes.
My bad.
So atoms make up the matter, and the atoms are made up of...
Protons, neutrons, and electrons.
Which are made up of...
Quarks.
Which are...
Little itty bitty tiny things that have really weird strange names, but luckily are not on your test and you don't have to worry about them. So, you need to know your 3 subatomic particles because there's totally a matching part on that to know what their charges are. And matter is going to keep coming back to haunt you for pretty much the rest of the time we're in physics, which is about half of this school year. So anything that has mass and takes up space is matter. If you've watched the videos, I'd recommend watching the videos. But if you've not watched the videos, one of them is really, really good and goes on to explain about the Big Bang. And contrary to what your textbook says and what you immediately jump to the conclusion of, the Big Bang was not an actual real explosion. It was something, but since we have no primary sources, eyewitnesses, or anything that actually watched it happen, we don't know what happened. No clue. The matter, don't know how it moved, don't know what it did, don't know what caused everything to begin, so we just refer to it as the Big Bang.
And just like every positive has a negative, matter has an opposite, which is antimatter. It behaves just like matter, but has opposite charges. So instead of the proton being positive in matter, in antimatter,
it's going to be negative, and it's actually called an antiproton.
And then the electron is going to have a positive charge, so it'll be called a...
It's actually called a positron.
So if you hear those words, you'll know...
During the Big Bang, matter and antimatter were both created. Obviously, we don't have much antimatter around us. If we ever have antimatter around us, it's because it's been artificially created and purposely induced. This is going to be because they were not created in equal parts. If they were created in equal parts, when matter and antimatter meet each other, they completely and totally destroy each other and cancel each other out and release an insane amount of energy. So that is why there are 1 billion particles of antimatter for every 1,000,000,001 particles of regular matter. That way,
they all cancel each other out except for the 1 particle of matter.
Yep, that's why it's left over, which is even crazier and stranger to think that everything in the entire universe is made of matter and all we are leftovers. About how much was created from whatever the Big Bang actually was. But you are going to need to know these numbers. It is a test question, and you're going to need to know which one was the winner.
I bet one of the choices would be 1,000,000 instead of 1,000,000,000. So maybe we really need to know billion instead of million.
Yes. Totally a test question, kiddos. No joke. Now, dark matter, this one's the easiest, because we know pretty much nothing about it. We are literally in the dark about what dark matter actually is. There's 3 things that we know for sure about dark matter. Number 1, it does weird stuff with gravity. That is the only reason that we even know it's a thing, because the second thing that we know about it is we can't see it. And the third thing that we know about dark matter is that there's a lot of it. That's it. That's all we know. We can't see it, there's a lot of it, and it does weird stuff with gravity. Next is dark energy.
This is probably the hardest question on the test. It gets missed all the time on the matching for my class.
Really? Sad day.
I wonder what's confusing about it.
Because the word energy is in the definition of dark energy.
They always want to say dark matter instead of dark energy. But if it's going to provide energy, it's going to have to have energy.
Right? Yeah, you need energy to do stuff like, expand the universe. That's going to take some energy, take some effort, and that's what dark energy does.
And since we don't know how it's happening, we're in the dark about it. So it's dark energy. Yes.
But yeah, that's what dark energy is. So those are three things that actually people really do commonly get mixed up are matter, antimatter, dark energy, and dark matter. So regular matter, anything that has mass takes up space. Antimatter, identical to matter, but opposite charges. That's what that prefix anti means. Then you've got dark matter. We're in the dark about it. Weird stuff with gravity. Can't see it. Whole lot of it. Dark energy. You need energy to do stuff, like expand the universe.
Electromagnetic radiation. Oh, this is one of the more you know highlighted notes, so it's going to be on the test. Energy that can travel through space in the form of waves. So it doesn't have to hit any kind of particles and able to do that. Electromagnetic. So that has electric and magnetic.
Like what we're talking about now in class, because this is going to come back to haunt you a little bit. There's maybe a whole chapter on waves that cover what's below this in the electromagnetic spectrum. It's because this energy, that is how it's going to move. It's going to undulate in this wave-like pattern. And right now, you need to know on this spectrum which type of waves have the longest wavelengths and which one have the shortest wavelengths. So you need to know radio waves have the longest, gamma have the shortest, and you also need to know that light is a spectrum. And we're back from an unexpected recess-related intermission. So, as I was saying, the electromagnetic spectrum also includes visible light. So the colors red, orange, yellow, green, blue, indigo, violet, also known as
Roy G. Biv.
Yes. Those are wavelengths. That's the only reason we can see them is because they're reflected back at our eyes. So the visible light spectrum, it has wavelengths as well. Red being close to infrared and violet being close to ultraviolet.
Which one of those has the most energy? Violet or red?
That's going to be the wavelengths that are closest together, so violet. But that will be in another chapter later on.
Yes. So that's close to ultraviolet, so ultraviolet will be right above it.
Yep.
Very good. Easy to remember. Optical telescopes. Okay, these, they work with our eyes, the things that we can see. And there are two types that you need to know. They are the refracting telescope and the reflecting telescope.
Oh, sorry. Those are the good ones. Those are the good ones.
The way that I always remember this, the difference between refracting and reflecting, is the reflecting uses the mirror and refracting uses a lens.
Absolutely. And the reason that I say reflecting telescopes are better is because mirrors, the bigger you make them, the more light they can focus and the deeper you can see into space and the more amazing, beautiful pictures you can get. And sadly, the lens, no matter how big you make it, at a certain point, its resolution and how much light it can gather, it stops. So whether it was 10 feet high or 10 stories, you might get the same resolution of image. So that's why mirrors and reflecting telescopes are superior.
Those are the best. Once upon a time, there was a place called the Soviet Union. It was the USSR. And they were the enemy of the United States.
And a lot of other people, too.
And a lot of other people. And this all started after World War II, when Germany was being broken up. A lot of things went toward the Soviet Union, and a lot of things came to the United States, such as the scientists were broken up and taken to two different places. And so those great rocket scientists that we have, they had some as well.
Mm-hmm. And this pretty much ended up being a competition of my dad can beat up your dad for whoever could get to the moon first. And I pretty much mean that literally. They were in a race, in a competition, because space was the final unexplored frontier. And we just had to be there, apparently, because, why not?
So the race is on. And who wins the first heat? The Soviet Union. This was the Sputnik 1.
It was the first artificial satellite in space, and it completely and totally terrified people in the United States. We thought we were being spied on. We thought the world was coming to an end because they were in space now, and we were terrified of communism. And we had to go to round 2.
Round 2, we were determined to defeat the Soviet Union. So we wanted to send a man into space first. But the Soviet Union was first again. We're really, really close. We're only a month behind, and we're going to at least get to the finish line first.
Mm-hmm. We closed the gap. We had the Apollo program, which was going to land a man on the moon safely, and we ended up doing that.
And returning them back to Earth, yes.
Absolutely. This was the idea of Mr. John F. Kennedy,
Yes.
which is why we have the Kennedy Space Center named after him. And what this accomplished is we sent unpiloted spacecraft, first of all, because we were actually terrified of the moon. At this point in time, we didn't know that our moon was solid. We didn't know if it was liquid. We didn't know if it was quicksand. We didn't know if it was rubber. We had no idea.
Yes.
Yeah, or that. Like, we were not sure. So we needed to, send some out there, boop the moon, and make sure that it was safe to actually send humans to. And after many Apollos, we sent Apollo 11 as a manned mission. And they went crazy once they got to the moon. They took back 842 pounds of samples. We took back more samples of moon rocks than actual human that we sent to the moon. And we even discovered through seismometers that there are moonquakes. So not only are there earthquakes, but there are moonquakes and tremors on the moon, which also slightly terrified them because we really hadn't detected that up until then.
We had not, but we had to find out if it would be safe to land on the moon. We didn't know if something would land on it and just sink right in, but like you say, sending the unpiloted spacecraft was a good test. One thing about it, think about all the math they had to learn to be able to get there and get back.
Lots of calculus.
Yes.
Lots of calculus. Since we sent unmanned missions to the moon, there are other unmanned objects that we send into space, and they can be insanely handy. These are space probes. There are two main kinds of space probes. We have our orbiters and our landers, and thankfully they took no creativity whatsoever in naming these. Orbiters.
Orbit.
Yeah.
Yes.
Landers.
Land.
There's no, sarcasm, no confusion here. It is that simple. An orbiter, because it's going around a planet, it's going to
Be up in the atmosphere, just orbiting around, flying around.
and taking lots of pretty pictures and maybe some samples of what makes up the atmosphere. Landers are legit going to
Crawl around on the surface of the planet, like there's one right now on Mars, right?
Yep, and that specific type of lander is called a rover. That's what allows them to move around, and it is the saddest little rover of all time because once a year, every year on its birthday, it literally sings happy birthday to itself.
Parallax.
Parallax. Sounds weird, isn't that complicated? It is the apparent change. Notice that word, apparent. That means it seems like it moves, but it's not actually going to move. And you can experience parallax. You've probably done this before when you're bored. If you stick your finger in front of your face and look at an object kind of close to you back behind your finger, if you close one eye and then close the other one, the object kind of looks like it moves. And if you look at an object way further back, and you look at it with one eye, and you close the other eye and look at it, don't turn your head because I'm cheating. That's the only way I can wink. But it looks like it moves too. And the closer the object is, the more it looks like it moved, and the farther away the object is, the less it looks like it moved. But you're sitting here, and you know the object didn't actually move. Believe it or not, this is a very similar method to how we study stars and galaxies in space. Not with our fingers staring at them in the sky, but with similar technology and very, very cool, amazing. What kind of telescopes?
Reflecting telescopes.
Reflecting telescopes.
So I paid attention.
You did indeed. I thought I was going to get you there.
One thing about the parallax, anybody that's ever tried to shoot and look through a scope, one of the images will stay in place more, and that'll be your dominant eye.
Mm-hmm.
That's the one you should use. I never knew that till I was older.
The more you know. Light years. Now we're going to get into the math. There's going to be a whole separate video for the math part, because I know some people cry when they hear math.
The more you know.
Yes.
Light year. Oh, that measures a year. So that would be measuring time, right? Oh, wrong.
Nope, you missed that one.
Light year measures
distance, people. Distance. Okay? Do not be tricked by that. It is a measure of distance. It is literally going to measure the amount of distance you would cover if you were able to travel at the speed of light nonstop for an entire year. Hence the name light year. And I've done a little bit of math for you, and that ends up being 186,000 miles in a second. So in 1 second, you would be able to go around the Earth 7 times and already be started on your 8th trip. Wow. In 1 second. And you're going at this speed for an entire year. And that gets you to a nice, little 5.8 trillion miles. The nearest galaxy to us, our sister galaxy Andromeda, is, I believe, it's either 2.4 or 4.2 million light years from us. To calculate that in miles, you'd have to multiply that number in millions by a number in trillions. That's a lot of zeros.
The one star that we have close by is the sun, and it actually takes the light of the sun a little over 8 minutes
Yep, to travel to Earth.
Mm-hmm. It's hard to believe.
That is true. Speaking of the sun, that was a nice segue there. It's like you knew we were going to be talking about that. It's a star. It didn't have a very fancy name. We named a lot of the other stars a lot cooler things, but we have the sun. We did the same thing with the moon.
I'm surprised we don't just call it star.
Literally.
No.
Legit.
Oh, there's star.
Yeah. The star looks lovely today. Yes. But most stars are big burning balls of hydrogen. That is the predominant element because it's a very simple and easy element to make. It's element number 1 on the periodic table. And they are big burning balls of hydrogen because hydrogen is insanely flammable.
Yes.
Second most popular element in stars is helium. It is number 2 on the periodic table as well. And there are some other like little trace elements, but we don't worry too much about that.
Hydrogen's number 1.
Mm-hmm.
1 proton. Helium's number 2.
2 protons.
2 protons.
Yep, and that is all you need to know about stars.
Wow.
And this, thankfully, is more nice, pleasant, common sense stuff. With brightness, think about it like a candle or a flashlight. The larger the flashlight or the flame is, the brighter it's going to be. The smaller it is, the dimmer it's going to be. The hotter the flame, the brighter it is. The cooler the flame, the dimmer it is. So it's at least very common sense stuff.
Yes, very much common sense. As long as you'll read this question, you will not miss it.
Yes, and read it slowly, because honestly, some of these questions, that'll be how you miss them, as you just don't read all the answer choices or you read too quickly.
All right, one more, the more you know that we have is due to the expansion of the universe, scientists believe that galaxies are traveling away from each other as the universe continues to expand. So the question might be, do scientists believe that the universe is expanding or coming in together? And the correct answer is?
Expanding. Think about it like the question from the bookwork, where it had the bread dough and the raisins, where the dough rises and expands and the raisins spread out. That's like the galaxy. The universe is expanding and galaxies are moving away from each other. Also, know that all the things in a galaxy are held together by gravity. Since we're studying gravity right now, it should make a lot more sense that it is a force that is able to pull things toward a center of gravity, and that's what they're all bound together by. I do believe that is another test question, too.
Yes. Anytime something is pulling in toward itself, it's always gravity.
Typically.